Is this on? Can I be heard? Am I audible there? Yes? No? Okay. Do I have to speak louder? Is that okay? All right. Thank you very much for this kind introduction. And giving me this opportunity to come here and talk to young students. When I get these invitations, I imagine that the students would at least be at the postgraduate or doctoral level. It's easy to speak to them, relatively. It's a little more difficult to speak to school children for two reasons. One, the formal amount of knowledge that you have at this stage is not very high, as you can expect, because you've just begun your education in some sense in secondary school. The second and more important reason is that it's the uniform experience of all of us in the educational field that younger students, school students in particular, high school students, tend to be very interactive in the sense that they question, they ask a lot of questions, they have a lot of doubts, they argue, they would like to get things clarified, they have no inhibitions at all. And I hope Ramaswamy spoke to you yesterday, and he too decided to scuttle his formal lecture and interact with students, and I can't do any better than to follow in his footsteps. So I would like to make this a kind of extempore speech, but at the same time I would like you to ask whatever questions you have, doubts you have, etc. With one statement made in the beginning, that you should not think that any question is a silly question or a frivolous question or a stupid question. There is no such thing as a silly question or a stupid question. All questions are valid. Many of them have answers, and if they don't have answers, they at least set people thinking. And I should tell you right away a serious fact which I'm sure all of you are beginning to slowly appreciate, and you will appreciate as you go along in your education, and that is your textbooks do not have all the answers to all possible questions. So it's not as if all knowledge is already there in the textbooks and it's only a matter of now reading those books as you spend more and more years in the system. That's not true. Most questions are unanswered. I like to give this example of a very famous physicist, John Wheeler, who made this analogy. He said our knowledge is like an island, and all the time the periphery of this island is increasing. So the island is growing in size. More and more is coming out of the sea, and the area of the island is increasing all the time. But he said we must not forget that as the area of the island increases, the perimeter of the island also increases. And the perimeter is the boundary between knowledge and ignorance. So as we learn more and more, we are also in a very real sense becoming more and more ignorant, because we have more and more questions cropping up all the time. So this is a never-ending quest, and that's the remarkable enterprise that we have all embarked on in the last few hundred years, namely the attempt to know the entire universe. So I'd like to start by asking all of you, how many of you are going to be science students, or already are science students? In the science stream, I believe you call it. Right? How many of you are going to be humanities or arts students? Just one. What about commerce? No? But you have to make a choice now at this stage, right? When you go to +2, you have to make a choice. How many of you intend to become science students? What do the rest intend to do? I mean, I see a lot of people not making notes. Now we are getting some action. How many people propose to choose the arts stream or the humanities stream? What would you like to do? She wants to become a classical dancer. Excellent, very good. So she already has a good notion of what she would like to do with her future career. And that's very good. How many would like to go into the commerce stream? No potential Bill Gates, no business people here. I'm surprised. How many people want to become entrepreneurs? No? If you want to become an entrepreneur, you have to be bold above all. So you have to raise your hand high. How many want to become entrepreneurs? Innovators. These are all terms that are coming up now. People are speaking about entrepreneurship, innovation, and so on. Okay, so the bulk of the students here are going to intend to do science. By science, I include also engineering. How many want to do engineering? Okay, that's a fair number. How many want to do medicine? Well, that's scientific too. Okay, so a fairly large number of people have some idea of what they would like to do. You already have some goal and you're going to work towards that goal. That's very good. But I'll also say right away and reassure you by saying that if you haven't chosen anything and you're all very confused, how many people are very confused about what to do next? How many are very confused? Good. Confusion is a sign of intelligence. Okay, that's very good that you're confused, because you should explore all options, and it's quite all right at this stage in your lives to be unsure about what you want to do next. I'm sure you're receiving a lot of pressure from various quarters saying you should decide, you should make up your mind and so on, but you don't have to do that. Take it from me, you don't have to do that. There are three reasons why your generation is going to be very different from that of your forefathers, of your parents, even your parents, and certainly of your grandparents. Okay. Reason number one, your longevity is going to be astounding by present day standards. So you people are going to live well into your 80s and into your 90s, if not more, because all the normal problems that beset us today, such as cardiac arrest or failure and so on, these problems would have been tackled to a good extent and solved. So that it's, barring accidents, there's no reason why people cannot live a very long time. And for the first time, we are going to be seeing a generation where the longevity is going to hit at least 90, if not more. That's number one. That's a long way off for you. You have at least 80 plus or 90 plus years from now on. So that's a long time for you to think about doing things. Therefore, no reason why you cannot have 2 or 3 different careers. I foresee that you are a generation where in mid-career you will have the option to change careers. You may do science, you may become an engineer. All of a sudden you may decide at some stage in middle age that you would like to write poetry. Perfectly all right. Or you would like to become a novelist. Perfectly all right. So these things are going to be much more accessible to your generation than in the past. That's number one. Number two, you will not have any retirement at all, because you've got such a long-lived nature of your life is going to be so long-lived that you will not have conventional retirement. You will work till you feel like working, till you're ready to drop. And that is going to be the pattern in future. There will be no official retirement date as such, except in certain things like the defense forces and so on. As far as careers are concerned, there will be no retirement, essentially no retirement at all. Then the next point, you will not have any local work time. The concept of 9 to 5 jobs is going already. Already there are lots of people in our country who are operating on American time or European time. They already are operating. Working hours are international working hours. So you will work whenever you can spare the time, wherever you are. You will not have a local workplace. Your local place, you will be networked in communication with people by video and audio so effectively that you will not feel the need to even travel. The necessity for travel, except for pleasure purposes or holiday purposes, will come more or less to a halt. You will get to a stage where you will have video conferencing There's no reason to travel, undertake arduous, lengthy travel in order to meet other people in the face. That's not going to be needed at all. So you will not have any local workplace. Your place of residence will be merely the place where you happen to keep your wardrobe. So that's crucial to remember. So no locality in space or in time at all, which means you're free and you can do whatever you like. And like I said, longevity will ensure that you will have 2 or 3 different careers. Given that, and that's obvious to anyone who thinks about what is happening, this is obvious that that's how the future is going to be another 20 years, 30 years from now. It's therefore surprising that we still are worried about making sure that young people settle down extremely fast. And this, I must say, is a peculiarity. It's certainly a peculiarity of Asians as a whole, certainly specific to Indians. It's very, very pronounced that people would like you to settle down very fast. Now, I don't see the reason why. You should make a few wrong turns, make a few choices of career which didn't work out, you backtrack and you go on to a new career. This freedom is available to your generation. So this business of settling down might have been applicable at one stage when economic circumstances enforced people to take up jobs very early in the day and start calculating retirement benefits by the time they were 25 years old. That's not true in your case at all. So I see no reason why you should settle down. In fact, as far as I can tell, the only thing for which settling down is a satisfactory state of affairs as precipitates in chemical reactions. They settle down and you'd like to settle down very fast. Only sediment settles down very fast. Everything else is in flux, in turbulence. And that's the way people should be. I don't see why they should settle down to placid, common lives if they can achieve great things. They should be able to dream and they should be able to do it. Okay. So, once you remove the constraints that have been there on people in previous generations, I think the sky is not the limit for you people at all. Then you're free to go as your whim and fancy takes you, but you have to remember one thing, nothing comes easy. Every single thing that you can achieve or do comes very hard. So there's no substitute for very hard work, for constantly being on the job, for thinking about things all the time. You cannot switch off your brain at any time. You have to be thinking, waiting for opportunities, looking for knowledge, acquisition of knowledge, putting it all together and thinking up new things. So this is a task which is pleasurable, but at the same time it's a little bit of pain mixed with it, because anytime you try to do something creative, there's a lot of pain associated with it, of course. And you should also have a little bit of a discontent with yourself that you can perform a little better. Of course, you shouldn't get into a tailspin and get into depression, nor should you be elated at the smallest achievement and stop working altogether. You can't do that. So while you can have a little bit of transient self-congratulation, it should not be a permanent state of affairs, nor should small failures affect you to the stage that you become completely depressed and go into a tailspin and switch off from the world. That's not possible either. But the equilibrium state is a state of slightly simmering discontent with your own performance. And let me assure you that that discontent is a sign of intelligence. The only things that are completely happy with their state of life are potatoes and vegetables. They are perfectly happy as far as we can tell. But human beings are not like that. You always are aspiring for something, thinking about something, and always has a little bit of discontent. That discontent should be directed inwards, towards yourself, and not for comparison with other people. There's no point in comparing yourself with anyone else at all at any stage, because that's not how this world works. Any comparison is inevitably odious and not correct in the ultimate analysis. So your competitor is yourself. You're fighting against yourself. You're trying to do a little better. And that's the approach which one should take in order to get ahead. Okay. Now that I've said these these generalities, let me come to specifics and let me talk about science itself. By science I include technology, I include engineering, I include medicine, I include everything you can think of. And let me also say in the same breath that as we progress, as knowledge progresses, more and more subjects are coming within the ambit of quantitative analysis. They are becoming more and more quantitative, more and more mathematized, if you know what I mean, including subjects like economics, and no doubt in the future even subjects like psychology and sociology. They are going to get much more precise, much more quantitative, much more predictable. So by science I mean all these things put together. Now this enterprise called science is remarkable in the following sense. There are no authority figures at all. What we are trying to do is understand the universe, the way the world works around us and the way we ourselves work. There are in this game no authority figures at all. Nothing is right because somebody said so. Newton's laws are not right because Newton said so. Einstein's theory is not correct because Einstein said so. All these people made mistakes. Every one of them, the moment the hubris reached a stage where they started telling nature how to behave, they fell flat on their faces, because nature is beyond all of us. It's bigger than all of us, and it yields its secrets to honest questioning and proper inquiry always. Nothing to do with authority figures. In this respect, the body of knowledge we call science differs drastically from other bodies of knowledge or other bodies of human creation, such as religion, for example, which is dogmatic, which has got a litany, and the word is written once and for all, and there's no question of changing it at all. That's the way it is because that's the way it is, nothing else. But science is not like that at all. It's self-correcting always. It is completely prepared to throw out its assumptions and impose a fresh theory or a fresh look, provided the evidence warrants it and requires it. So in that sense it is self-correcting. It subjects itself to scrutiny all the time. It is being tested all the time, and the links are always being tested to see how strong they are. And then more and more of the subject gets unified as you go along. So while in your school education you have this separation between physics and chemistry and biology and mathematics and so on, these are largely for purposes of convenience. As you go to higher education, you begin to realize that it's very hard to tell the difference or to catalog something into a particular subject. After all of chemistry is based on understanding the concept of valence. But valence is a quantum chemistry concept. It's a concept in quantum mechanics. It cannot be understood classically. So right there you have quantum mechanics at in a very serious way appearing in fundamentals of chemistry. So would you call this physics or chemistry? You could give it a name, you could call it quantum chemistry, but it's actually based on quantum mechanics, and it applies to real substances, and it takes a theory called quantum theory, applies it to real substances. Take a subject like gravitation, about which there's been a lot of buzz recently due to the gravitational wave, the LIGO. This thing here was a theory which was propounded by Einstein, who related the gravitational field to what he called the curvature of space-time. But that idea of curvature of space-time, curvature itself of spaces, was already known much earlier to people like Gauss and Lobachevsky and so on, and Riemann had actually in the 19th century evolved a complete mathematical theory of what we call Riemannian manifolds or Riemannian geometry today. And it turned out that that was precisely the mathematics that Einstein needed to understand gravitation. So would you call this mathematics? Would you call it physics? What would one call it? Or mathematical physics? It doesn't matter. Doesn't matter at all. Let me give another example from physics. In the 1920s, a subject called quantum mechanics was stumbled upon, was settled. The basic principles of quantum mechanics were all set down in the 1920s, and over the next few decades the subject progressed. It's still in progress. It's still a house under construction after nearly 100 years after it was started. But we understand a great deal, but we also don't understand a great deal more. Now this subject called quantum mechanics requires a certain kind of mathematics. Just the original people who wrote down quantum algebra. Again in the 19th knowledge or mathematical knowledge called linear algebra, and that's precisely what was needed. Linear vector spaces were precisely what were needed for quantum mechanics. So would you call no, but the fact is that there is an exact natural language which was evolved from the mathematical point of view, which fits in beautifully to understand physical phenomena and fits in with the postulates of quantum mechanics and helps give them power to be able to make calculations and make predictions, etc. So you see that these things are all very closely linked to each other, and it looks like, for some reason which we've not fully understood, it looks like the more we delve into it, the more we realize that the universe seems to be kind of mathematically constructed, that the language you need to understand it is ultimately, at bottom, not normal language, not normal semantics, not any specific everyday language, but the language of mathematics. Because mathematics is language plus logic. So there's a certain degree of logic that's needed when you want to make progress in science, and nature seems to use it, and the logic is mathematical in nature. So once again, the normal question that arises in the minds of young students is, what is mathematics and what is science? Are these two separate? Are they two completely separate from each other, divorced from each other? Or even more deep question, is mathematics a creation of your mind, the human mind, or is it there in the universe somewhere, and all we're doing is uncovering part of it? So is there pie in the sky, little pie in the sky if you like? Is there pie in the sky, or is it a creation of the human mind? Is the whole thing a creation of the human mind? This is a deep metaphysical question to which there is no definite answer as yet. But the personal belief of most people who thought about it is that it's a little bit of both. There is mathematical structure in the universe. Our brains are also hardwired in such a way that we can understand this language, and therefore this will come together. And whether it's entirely in the mind, no. Whether it's entirely out external to us, no. I think it's a little bit of both, and that's a happy marriage because that's what helps us to go forward. So these are things which one thinks about after one understands a little bit of science, after one acquires a little bit of information, so to speak, on different parts of science, then the unity of the subject starts appearing. I'm afraid that this is not immediately apparent from your textbooks. It's not, if you look at your textbooks at this stage, it's not clear if the chemistry that you see is related in any way to the physics or to the biology or to the mathematics. But let me assure you that they are all closely linked to each other in manners which are completely surprising and which we have not your vision for the future. My answer to that is somewhat different from the common answer. One can of course sit down and list all the things that you think are important. That would be a very personal statement. But I think the answer really should be, to have vision of the future, you should have good vision to start with. You should have 20/20 vision. But people my age already have failing vision. So there's no way in which we can see what's going to happen in the future. Because certainly when you people have your careers, a few decades from now, you will be working on subjects which don't exist at the moment, and which I don't know what the words would be, what the spelling would be, what the meaning of those words would be. So it's impossible for an older person to make a prediction. The subject is always taken forward by young people, by young pioneers. All that one can do is to expose them to all these little features and say that all this exists, these are interesting connections, perhaps you would like to explore that. That's the spirit in which you should take all the instruction that you receive from your teachers, that they're merely pointing your way to the future, and not that they're giving you a body of knowledge which is complete in itself, all questions answered, etc. So, I urge you to ask as many questions as possible, get your doubts clarified, and do not hesitate to expose your ignorance. Ignorance is something you should actually not bother about. You should wear it proudly on your sleeve and say, look, I don't know, but I need to know. I want to know. Okay. Do not worry about asking questions to which you already know the answers. Don't worry about whether when you ask a question, your peers will think that you're stupid, because like I said, there is no such thing as a stupid question. And above all, remember that a lot of the progress in science came because some young people dared to ask questions which had never been asked before, and which their peers no doubt thought was a stupid question, but they turned out to have the germ of inquiry which led to future inquiry and development of the subject. So remember this, if you don't know something, you should get it clarified. You should talk to people, you should ask people who are knowledgeable, you should discuss among yourselves and get it clarified. Because the state of ignorance is not a very comfortable one. Because when you go to bed at night, you and the pillow know that you don't know. And that should make you very uncomfortable till you find out for yourself. Each of us understands things in his or her own way. No two people understand something the same way. When you say the color red or a shade of red, the shade is perceived differently, we know now, by different people in different ways. It's like the psychology of vision also plays a role. It's not just the physics there. The interpretation by the brain differs slightly from one brain to another as to what you would describe a shade to be. And this is the way everything works. All knowledge works like that. All information is processed by different brains in slightly different ways. Some people think very geometrically. Everything is in terms of pictures and they can visualize three-dimensional objects very easily and so on. Other people think algebraically. They think in terms of symbols, the equations speak to them and so on. There are other people who think very qualitatively. They think metaphorically in terms of analogies, in terms of metaphors and so on. So there are different ways in which different people think, and the happiest is the collaboration where you bring all these people together and you bring in to bear all the armory that several people have in order to tackle a problem. All the major problems these days are tackled by collaborations. You have to talk to peers, you have to discuss, you cannot work in isolation. The days when scientists sat in an attic somewhere locked away for 20 years and produced the results which they wrote in code are gone completely. Today science is more or less an open book, and it requires a great deal of discussion, collaboration, talking to people, learning from other people, and above all, teaching other people. Knowledge is the only thing that grows when you share it. So teach other people. If you ask me to give one piece of advice to young people, I would say, teach your peers. Teach children, your younger siblings, teach other smaller children. Because that way you become sure that what you know is sound. Every time you teach, your knowledge improves. Your understanding of what your knowledge is improves also. And this is, it's an open secret that most of your teachers would agree with this, that the time that they actually learned the subjects they're concerned with was when they started teaching that subject. As a student, one doesn't have the perspective, one doesn't have the time to digest the information and acquire a perspective on the subject, but as a teacher, one acquires that perspective. And every time you meet a fresh bunch of students and they ask you new questions, you learn this a little bit better. You get a fresh angle and a fresh insight on what this is all about. You begin to understand things a little better. A process which has no end at all. So I would urge you to ask questions, to talk to people, and to let people know what you understood. Talk to other people, discuss things with people. Those students who succeed in exams are just one part of it, they're necessary evils in some sense, not the best way to test young students or the understanding of young students, but it's a system we are stuck with, we're there, so let's not get into the good and bad of it. But the fact is that this exam system, bad as it is in many respects, helps also to discipline your mind. You have deadlines to meet, you have to understand certain things in a focused way. To that extent, this system is a good one in some sense. It does have its positive points. But the real understanding comes when you teach other people, when you discuss with other people. And you'll also notice that those who've done best later on are not those students who are necessarily at the top of the class. They are good, of course, but they're not necessarily those people who have taken a secret bunch of notes and have studied it, learned it by heart and reproduced it in the exam. No, it's the people who go from one student to another, one group to another, acquiring information here and trying to impart that information to to somebody else. So you upload something here, you download something there. Those are the people who succeed in the end. And that's what you should aspire to be. What you should do is to be an absorber of knowledge, but equally an emitter of information and knowledge. This is very, very important. So these are some homilies which I've tried to share with you. I assure you that I didn't follow any of these guidelines or precepts or something like that, much to my regret. We didn't have much guidance to start with. But today in this world, you have a large amount of sources of information. You always have Wikipedia, you have Google, you have many, many sources of information. But you should also be judicious enough to realize that all of it is not necessarily correct. You have to have independent verification of things. But the information is there in the internet. It's already there in staggering amounts, more than a human being can process. But you should know what to select and what to look at and how to choose judiciously. So these are some general tips that I thought I would share with you, some thoughts I thought I'd share with you. But now I'd like you to express your opinions and comments, and feel free to say anything at all, to ask anything at all. I can respond. Yeah. What is quantum physics?
Quantum physics.
Yeah. He's got a good question. His question is, what is quantum physics? Well, I must go back a little bit in history. It turns out that by the end of the 19th century, people had a fairly good idea of two major branches of physics at that time. Three, as a matter of fact. The first was, they had a fairly good understanding of mechanics, of what happens in what we today call Newtonian mechanics, classical mechanics. This controls the behavior of machines, pulleys, levers, objects, macroscopic objects, projectiles, things which move at reasonably slow speeds, fairly massive objects on this earth, for instance. It also led to an understanding of the motion of the planets through Newton's inverse square law of gravitation. That too is a part of mechanics. So what we today call classical mechanics encompasses that body of knowledge, and they had a fairly deep understanding of it. Had been built up by the end of the 19th century. Then there was a class of phenomena associated with electricity and magnetism and light. This too looked like a body of disparate phenomena in the 17th and 18th centuries, till somebody called Maxwell came along right at the end of the 19th century, and he unified all of electromagnetism. Electricity and magnetism, he showed, were part of the same phenomenon. And light was also identified as an electromagnetic wave. So he unified electricity, magnetism, and light, or optics. And that was the first and second great unification in nature. The first was done by Newton when he showed that there's a universal law of gravitation. So the same thing that makes projectiles fall on this earth is what makes planets go around the sun, etc. That was the first unification. The second was the unification by Maxwell of electricity, magnetism, light, etc. So these two mysteries, in some sense, were under control. There was a third kind of phenomenon which had no explanation right through the 16th, 17th, etc. centuries, till again the late 19th century, and that was the phenomenon of heat. Nobody understood earlier what heat really was. They thought a hot body contains some magic fluid, and that fluid seeps out and cools down, and that's how an object cools. It transmitted to other bodies, they get heated up, etc. There were many theories propounded, till thanks to the efforts again of Maxwell and people like Boltzmann, etc. It was understood by the end of the 19th century that heat was another name for the energy associated with random molecular motion. So we began to understand that matter was made up of molecules, very small particles, and then atoms for these molecules a little later. But then these were all constantly in motion, in agitation, and that random motion's energy is what manifests itself as heat. And the laws of thermodynamics were written down. So by the end of the 19th century, we had a very good idea of what these three classes of phenomena were, and that more or less took care of all the phenomena that we saw around. But then there arose, and this is now today called classical physics. But then there arose phenomena as people probed deeper and made experiments which did not fit in with these in these three bodies of knowledge. One was what happened when objects move really fast, very tiny objects move really fast. What would happen, what about Maxwell's equation itself? They are not consistent as they stand with the idea of light corpuscles moving according to Newtonian mechanics. So there was a conflict right there. There were other conflicts that came into prominence, such as the black body radiation or the photoelectric effect. There were experiments done trying to extend the laws of heat and mechanics and electricity magnetism, and they failed. The failure was dramatic and absolute. All possible fixes did not work at all. So right through the beginning of the 20th century, 1910, 1920, almost 20, there was complete confusion and people didn't know what to make of these new phenomena. And then tentatively this postulate of light traveling in quanta of energy was made. So it started very tentatively with some postulates saying that light energy is carried by quanta of energy, and there were other experiments such as the photoelectric effect, and then there was a theory given by Bose for black body radiation, all of which fitted together, but yet there was no satisfactory merging of all these things. And then miraculously, around the year 1925-26, several people, most notably Schrödinger, Dirac, Born, and Heisenberg, and a few other people, put together this theory called quantum mechanics. It was a set of rules to start with, and it evolved. A little later, it was made in terms of postulates. So you postulated certain starting points, axioms, and then you saw what the consequences were. This is not Newtonian mechanics. It flies in the face of Newtonian mechanics. The rules are very different. For instance, it says that a particle like an electron cannot have a path in space, because if it has a path, you know at every point instant of time both its position and its momentum to infinite accuracy in principle. That violates quantum mechanics immediately. It led to something called the Heisenberg uncertainty principle. So you had a large number of these non-classical effects that began to be seen, but they satisfied certain postulates, consistent set of postulates called quantum mechanics or quantum theory, and more important, they started explaining what happens on the atomic scale, such as the spectra of radiation emitted by various atoms when they are excited, black body radiation, and so on. And over the next few decades, successively, quantum mechanics was applied first to molecular physics, then atomic physics most importantly, and then nuclear physics, and subsequently in another avatar called quantum field theory to subnuclear physics, and now to condensed matter physics, solid state physics, etc. So the universe we now think, at least the present state of knowledge, is governed by quantum physics, by quantum mechanics. Then you could ask, what about Newtonian mechanics? Do we throw it away? Not at all. It turns out that Newtonian mechanics or classical mechanics is an approximation to quantum mechanics applicable to large objects moving relatively slow compared to the speed of light, etc. So it is not that Newtonian mechanics is wrong, but that its range of applicability is limited. And you could ask, what's the ultimate theory? So today the idea is that it's quantum mechanics in various forms, but that could be changed in future. So it has subsumed classical physics, but retained it as a limiting case, just as Einstein's relativity subsumed classical mechanics and retained it as a limiting case when objects move slow compared to the speed of light in mind. So quantum physics and relativity are the two pillars on which modern physics rests. They have been combined into something called quantum field theory, which has been the most successful theory of all that we've had so far, but yet it's not a final theory. It's incomplete in many ways. For instance, we don't understand how to include gravitation in this theory at all. So there are many open questions. That will lead us to the next stage. So does that answer your question in part? It's unfortunately, quantum mechanics is expressed in a mathematical language, and we can see why it cannot be expressed in normal language. It cannot be. That's an impossibility to do. By its very nature, it's an impossibility. So the intrinsic language of quantum mechanics is mathematics. One can kind of read out those equations in words, but that would not give you any further meaning into those equations. That's the way it is.
Any other questions?
Sir, yesterday we asked two questions.
Yeah.
Is there any particle which can travel faster than light? We should be asking that today.
Is there any particle that can travel faster than light?
Yes.
Okay.
Another is if all the planets come on a line, straight line, what will happen?
If all the planets come in a straight
Common
line,
line, yes.
as seen from the Earth,
Yes.
they're not in a straight line. As seen from the Earth,
Maybe yes.
as seen from the Earth. That's an accident that happens once in a while. The second question is easier and shorter to answer. What happens when the planets come into conjunction with each other? Right? Nothing. It's obviously going to happen once you have all these planets moving in orbits. Then there would be these coincidences once in a while when viewed from any given point. And it must have happened many, many times in the past, and as far as we know, the world didn't end then. Right? So nothing special happens. Of course, gravitational forces would increase instantaneously because of that conjunction and so on. But the orbits are still stable for all practical purposes, so nothing much happens. So that's not a very serious, it's not a very significant phenomenon even in astronomy. On the other, I mean, maybe it's significant in astrology, which is, there are two topics which I'm prepared to discuss any subject, anything whatsoever.
So is there a relationship
But I'm not prepared to discuss two subjects because it would take me too long to tell you why they're completely bogus or pseudoscientific. One is homeopathy and the other is astrology. So unless you want to have a fight or you have all day to argue, you will not get into those two subjects.
Fine, that ends the answer.
No. Tell me. No.
Is there any real relationship between astronomy and astrology?
No. Let me tell you, there was another question about particles traveling
Yes.
faster than light. But let me tell you why astrology cannot be right. Many reasons. But one of the reasons is the following. And it's actually a very strange reason. You would normally have heard people who don't believe in astrology telling you that, look, those planets are very far away, they cannot affect you here. There's no way they can affect you. Therefore, astrology cannot be right. They're not right. They do affect you. Everything affects you. But the point is, because there's something called chaos in nature, everything affects you. Every single thing. In fact, chaos is such a pervasive thing that because you have so many effects, you cannot predict what happens if one particular cause changes. That's the problem. It is so delicately balanced. After all, let me look at it this way. You have the gas in this room. There are nitrogen molecules going around, bouncing, hitting each other and so on. Two molecules hit each other. Molecules in this room undergo collisions roughly 10 times a picosecond. So every 10 to the 13 seconds, that molecule is bumped and hit and sent in some other direction, then it's sent in some other direction, completely random. Now, if I can do something to prevent two molecules from hitting each other, any two molecules, but slightly move away, then the entire history of the gas is changed in principle. So you could ask, what force should I apply to a molecule so that instead of hitting another nitrogen molecule, it moves away by one diameter of a nitrogen molecule, so it misses it. It turns out that if you move one electron 10 to the 26 meters away at the other end of the universe, by 1 centimeter, then the gravitational force exerted by that electron, and that's a very weak force, 10 to the minus 40 compared to the other force, electromagnetic force, exerted by that electron on the nitrogen molecule here, is such that in about a couple of picoseconds, this molecule's trajectory is changed. So everything is connected, everything does affect it, and so on. Somebody sneezing in Indonesia can set off a turbulent little whirlpool here of air, an eddy here. So it is precisely because there are so many causes that you cannot disentangle the effect of any one cause and say Jupiter moving somewhere or Saturn moving somewhere else, your future is affected. It is affected, but not in a predictable manner. The whole point about astrology is that it claims to predict the future. And that's completely where it goes wrong. Nonsense. So as long as it stays with astronomy, that's fine. But the moment it says I'm going to predict what happens next, it's a chaotic universe. Not predict. Can't even predict the weather 2 days in advance for technical reasons. Now this business of particles traveling faster than light, first of all I must tell you that the word light really connotes the fundamental velocity. So what the theory of relativity says is that there exists a fundamental velocity in nature which cannot be exceeded by material objects. That velocity happens to be the velocity of light in vacuum, because light consists of particles whose rest mass is zero. The fact that there is such an entity called light which travels at that fundamental speed is very good for us, because then we can explore the universe. But mathematically it's not required at all from a mathematical point of view. So light travels at speed slower than little c inside a medium. There's a refractive index. So clearly inside a medium, light is not traveling at 3 times 10 to the 8 meters per second, but slower than that, divided by the refractive index. But that is not a free velocity, because what is happening is light in a medium is constantly absorbed and scattered and re-emitted by the atoms in the medium, the molecules and atoms. So it's not the straight path at the molecular level. So its effective speed is reduced. So I will call it therefore the fundamental velocity c. Now the question is, can you have a particle in vacuum traveling at a speed higher than little c, the fundamental velocity? The answer is, surprisingly, relativity does not forbid it. It doesn't forbid it. It's perfectly all right to imagine such particles to have such speeds and so on. But the question is, A, can you consistently build a theory of such particles? And B, how will you detect them? How will they interact with us? That is where the problems start. These particles are called, hypothetical particles are called tachyons. Tachy means very fast, making tachycardia and so on, so fast heartbeat. So tachyons are not forbidden by theory. They're not forbidden. But they cannot be consistently incorporated to the theory we have of sub-luminal particles. For instance, causality gets affected. The difference between cause and effect get interchanged. We know in this world that if there is an effect, it will always follow the cause. It's not as if I throw a ball to you, you catch it after I throw it. It's not as if you catch it and then I throw it. That doesn't happen. But that relationship between cause and effect gets perturbed, gets disturbed in a manner which cannot be consistently reconciled once you have tangents. So the interaction of these faster than light particles with slower than light particles so that we can detect them is questionable. I'm sorry, is this wrong? So that's the second problem. So there's a difference between actual observation and something that's forbidden by the theory that we have. And here in the strange case of tachyons, it's not forbidden by theory, but we haven't seen any. And we cannot reconcile it consistently. Although, by the way, there are experiments which search for these tachyons. So you have now device experiments which will detect such particles, and we haven't found.
Any other question?
Yeah.
Yeah. There are so many questions coming up. Yes.
Yeah.
Please, can you pass on the mic? Yeah, please. Give.
So, sir, I vaguely read about matter and antimatter.
Yeah.
So, particles, antiparticles. I want
Yeah.
to know whether antiparticles really exist naturally. Can they exist?
Uh-huh. Well, the belief is that, first of all, two things. All elementary particles have antiparticles. Some elementary particles may be their own antiparticles, such as photons. A photon is a quantum of energy called electromagnetic radiation. It is its own antiparticle. On the other hand, the electron has an antiparticle called the positron, which differs from it in charge. Now, there's a theorem which says, there's a result in field theory which says that if a particle has some rest mass m, then its antiparticle is guaranteed to have the same rest mass. So it's not as if antiparticles are repelled by gravity and particles are attracted. No such thing. All particles and antiparticles, particles and their own antiparticles have the same rest mass, always. Then, if a particle is unstable, it has a certain half-life, it decays radioactively, the antiparticle also has exactly the same half-life. These are results that can be proved. Now the question is, where are the antiparticles? We can create them in the lab because matter and energy are interconvertible. So if you have sufficiently energetic gamma rays under suitable conditions, you can produce pair production. It's called pair production. You can produce a pair, electron and an anti-electron or positron pair. And similarly, they can recombine to give you a gamma ray, two gamma rays, etc. So this is possible. And it's been seen. We know antiparticles exist. Now the question is, what about nature? Do antiparticles exist in nature? If you say they are stable, like the electron is stable, then they should exist in nature. The belief is in the early universe, when the universe started after the Big Bang, there was an equal number of particles and antiparticles. But then something called the asymmetry took over, or the baryon asymmetry. There are other technical names for it. And the antimatter got annihilated, destroyed. Matter dominated. Now, it's still an unsolved question as to how this domination occurred. How did it start? What was the seed of this? There are mechanisms for it. In technical terms, things like CP violation, etc. There are technical terms in particle physics, mechanisms in particle physics, which hopefully explain why we have a preponderance of matter today and not antimatter. So this is but the question is still open. We don't understand the baryon asymmetry fully, although we have some theories for it.
Next question, please. Yes.
Why does Kurungi flower bloom in once in 12 years?
Once in
12 years. Kurungi flower.
I don't know. I don't know why once in 12 years. I mean, that must be a long standing. I mean, there must be a biological cycle of some kind, but I don't know what the physical reason for it is. I don't know what the evolutionary reason for that is. I don't think there's anything sacred about 12 as such, but I don't know what the precise reason is, why it's such a long life cycle. Some evolutionary reasons, the survival, I don't know. Most phenomena in biology are that kind of question. Most of them have answers which are based on evolution. They're survival, fitness questions. For instance, why do we see very well in the yellow region? Our vision is most acute in the yellow region, yellow-orange region. Why? The simple evolutionary reason for it. We are not nocturnal animals, we are daytime animals. And the sun happens to be a star which is emitting radiation primarily in the yellow region, in its present state age. Okay. So evolution has seen to it that our visual acuity is best in the wavelength which is maximally put out by the sun. So it evolved once again. And that's a perfectly good evolutionary reason. And I think that this other question also has a similar answer.
Yeah, can you ask? Yourself. You are the mic.
What is dark matter and dark energy?
What's dark matter and dark energy? We don't know. We don't know. We don't have a clue. We have guesses. but we don't have a clue. Now, dark matter has been postulated to exist because of the behavior of the rotational speeds of stars at the ends of galaxies. You have these spiral galaxies, and we know what the velocity distribution of these stars is as you go towards the center. But the observed distribution is not consistent with what we know about the mass of that galaxy, the total mass of whatever is in the center attracting the stars, and so on. So the fact that the velocity spectrum, as we go radially outwards, does not match what we can deduce from gravitation theory, says that there must be a hidden source of gravitation which is not emitting light or interacting in any other known way with the normal matter, and that must exist there and exert a gravitational force. That's dark matter. Dark energy is much more than that. Dark energy is believed to be about 75% of the universe, 70% of the universe. It is a term given for what we know in quantum theory as a quantum fluctuation. It's called a vacuum energy. It is physically responsible, we think, for the fact that the expansion of the universe is accelerating, is increasing. So we think there's a kind of repulsive component, a repulsive force. We don't quite understand it, so we know even less about the true nature of dark energy than of dark matter. We don't know. Unsolved problem for you to solve.
Actually, I've heard that the on-road vehicles have an engine efficiency of nearly 20 to 30%.
What vehicle?
Vehicles which travel, which we use to travel, cars, buses, which use petrol. Petrol engines have an efficiency of nearly 20 to 30%.
Okay.
And actually, race cars also use the same fuel, but actually they are much more, seem to be much more efficient. They travel much more faster.
But they're streamlined, they're not built for comfort, they're built for carrying a very small payload, namely the driver. And you have an enormously powerful car carrying an extremely small payload, and it's made as light as possible, right? So, in a passenger car, and this is a general answer, common sense answer, I'm not an engineer, but in a passenger car, you would not aim so much for maximum speed as you would aim for comfort of the passengers inside. You would have a lot of shock absorbers, you would have ensure that the load increases, but you just want to make people get into a comfortable ambience. And that's one reason why the vehicle as a whole is more inefficient. You're not doing this to optimize payload versus the speed or anything. So that's a general answer, but you have to ask an automobile engineer. It's not as if the race car has a totally different mechanism altogether. It's still an internal combustion engine built along similar lines. The basic principles are still the same. It's not a separate secret source of power or anything. It's engineering for a purpose.
What if it created that is the mixing of hydrogen and oxygen?
Can water be created by mixing hydrogen and oxygen? Yes, of course you can.
No, that is scientific. In the lack of water, today we have seawater, and in the same way, if we can make a water which does not have any other thing and it is pure, just by combining hydrogen and oxygen.
This question is, can I take an oxygen cylinder, hydrogen cylinder, combine in some process and make water out of
So
it?
the same issue too.
The answer is yes, of course. Of course you can. You can create water. You can combine hydrogen and oxygen under suitable conditions. You can undergo the forward chemical reaction to make water, just as you can electrolyze water to get hydrogen and oxygen back. The question is, what energy are you expending in getting the raw materials in pure form and then combining it with it? It's not efficient.
Okay, last question, please. Yes.
What is a black hole and what happens if we go near to that?
Well, we have a theory of space-time called Einstein's theory of gravitation, which says that matter curves the space around it, in the sense that it's not Euclidean geometry that's applicable anymore. The question is, what happens if the matter's density is so high, so much matter is packed into such a small volume? What will happen in the limit? And the theory predicts, Einstein's theory predicts, that you'll have what's called a singularity. So at some stage, well, we're talking about black holes, so So at some stage, the gravitational field, the self-gravitational field becomes so extreme that this matter collapses upon itself. Everything gets crunched together and forms a singularity. Now that's a theoretical prediction, but we know a lot about it because we've analyzed the equations, we've seen what be the consequence of these equations, etc. It turns out that we don't still know for sure whether there's this actual singularity, but which will be a singularity is a mathematical concept. It says that finally this object will be point-sized and will have infinite density. Now, of course, infinity is a limit. It's not something which is attained in a finite time. We're not sure. We're not sure if once you get below about 10 to the minus 35 meters and the density becomes enormous, becomes what's called the Planck mass equivalent, then we're not sure if classical physics is applicable anymore. We are reasonably sure that quantum mechanics must be applied to gravity. And when that happens, we don't have a satisfactory theory. So classically we have a singularity, but quantum mechanics, and we know quantum mechanics is right, it's been right in so many other places, we're not sure. We don't know as yet. So right now it's just a theory. However, the existence of black holes has been indirectly seen in many ways now. The recent gravitational wave that you saw fits in with the hypothesis that two black holes merged with each other. The two black holes had solar masses. They were equivalent, energy equivalent of 29 and 36 times the mass of the sun. They came together, and in that process they created a bigger black hole, a more massive black hole, whose mass was 62 solar mass effectively. So the energy equivalent of 3 solar masses was emitted as gravitational radiation in this process, the extremely violent process. And 1.3 billion years later, we were able to detect a very faint chirp in our apparatus. So it suggests that we are on the right track. Predicted gravitational waves, we were able to detect the signature of it correctly, build a detector and look at it. Right? So this shows that such events, such objects do exist. Today the belief is black holes are much more common than we had thought. In fact, we think that at the center of every galaxy there is a black hole. Certainly at the center of the Milky Way, all evidence points to the fact that there is a big black hole. So black holes are believed to come in many mass ranges. They would start with about 8 to 10 solar masses, right to so-called supermassive black holes, which are like a billion times the mass of the sun. Those are the fellows sitting at the centers of galaxies. Pardon me?
Higgs boson. God particle, Higgs boson. Higgs boson.
Higgs boson. Yeah, this word God particle, as you know, would have read from the popular press, is a misnomer, because this was a particle which was predicted to exist by the theory, so-called standard model of physics. It is predicted to have spin zero, spin quantum number 0, rest mass not 0 but some positive number, and various other characteristics, various other quantum numbers, which are too technical for me to describe here. But the theory required it and nobody had seen it. So Leon Lederman, who was one of the great experimental physicists involved in particle physics, said, where is this goddamn particle? And this got published in the newspaper and they left out the damn. And they said, where is the God particle? And the name stuck. It became, where is the God particle? It became even more stuck when people realized that you needed to have this particle. The theory said you need to have this particle, you would have heard this phrase, to give mass to the other particles. This Higgs particle is supposed to be the reason why all other particles have rest masses which are positive, not 0. There's a technical reason why that is true, but it's not as if this particle is directly giving away its mass to the other particles. So there are several Higgs particles. Peter Higgs in the 1960s gave a theory, predicted this from quantum field theory. So did several other people, 5 other people predicted it at the same time. And the name Higgs particle got stuck because a little later Steven Weinberg wrote a paper in which he called it the Higgs particle. And so the name got stuck. So the word God particle is sheer accident, and the Higgs particle is for historical reasons, nothing more. But There are several kinds of Higgs particles, and we've seen one of them. People are still studying where the others are, which particular Higgs particle this is, and what theory does it fit into, etc. Are questions which will be answered in the coming years. Research is still on, very much on. Yeah.
Molecular electronics, molecular devices, and so on. Devices are also getting smaller.
Yeah.
In which case, I want to know, can quantum physics or quantum mechanics predict a priori what would be the difficulties in shrinking the sizes?
Yeah.
And how can we make it more efficient?
Yeah.
In making a business?
Yeah. The question is there a limitation in size? Yeah, there eventually will be limitation in size. Molecular electronics is, as the name suggests, it's electronics at the molecular level, single molecular level, or the few molecules, etc. The difficulty, the limitation, the principal limitation, I'm not an expert on this, but the principal limitation here would be the way the device would dissipate heat. Because today we know that every computation costs heat, produces heat. There's dissipation always needed. And once the scale becomes extremely small, then the heat dissipation will become a problem. How does it dissipate heat? And what the heat dissipation will do is also to destroy what's called quantum coherence. So this possibility of doing quantum computation or using quantum mechanical tricks in order to do computation on build devices is severely limited by the fact that we don't know what to do with the inevitable dissipation at that level. So theoretically there seem to be some limits below which we cannot go. But we don't know. It will be a totally new idea which might take you beyond that.
Yeah. There are only one question I can just allow.
So we know that during refraction of light, light bends, the velocity changes.
Yeah.
What actually causes the velocity change? Means what is the molecular picture? What is happening?
Yeah, this light, as I said, this photon is absorbed by the atoms in the medium or the molecules and re-emitted. So this process of absorption, re-emission, if you like, multiple scattering of these photons is what causes the effective speed to be reduced. It's like walking in a crowd or electrons moving in a conductor. You apply voltage in a resistor and the electrons by and large move in one given direction. But the velocity with which they move, the instantaneous velocity is much higher than the drift velocity that you have. Because in a crowd you're constantly being jostled, and while you may drift along with the crowd, your drift velocity is much, much smaller than the actual velocity between collisions. So that's the reason why this appears to be slowed down. In fact, it is slowed down to such an extent that there's a very famous question which one asks, a little trick question. We know that light takes 8 minutes to come here from the surface of the sun to reach the earth. So it's 8 light minutes away. The sun's diameter, the radius is about 800,000 kilometers. So we can calculate the time it takes light to travel 800,000 kilometers from the center of the sun to the surface. So if I ask, what's the time it takes on the average for a photon from the center, emitted at the center of the sun to reach the surface of the earth, you would add 8 light minutes plus the time it takes this to run this 800,000 kilometers. Be completely wrong, because it takes on the average 1 million years for a photon to start from the center of the sun and reach the surface because of multiple scattering all the time. So the speed is slowed down enormously. And the reason for speed being lower in media for photons is precisely this, that it is not the instantaneous speed in vacuum, but rather the effective drift speed after all those multiple scattering events are taken into account.
Okay, there are no questions. I think
there was one more. Somebody.
One more? There are many actually.
Okay.
So we're running out of time. Maybe you are not asked. Just.
Why on full moon day the tides of the ocean is high?
On full moon days?
That's a good question.
I knew the explanation of this, but I don't remember the correct one now, right now. It has to do with the fact that there is a simple explanation for it, that much I can tell you. I'm trying to think of the precise role played by the sun on this. I draw a figure and work it out. But
Dr.
it's a
Aruna
real
answer
effect.
this question?
Yeah, some.
Can you answer this question? No. Okay. Right. Right. I think we can allow 2-3 more questions because of the enthusiasm. Yeah. Please, you.
So what's the most believed theory of about the creation of the universe?
What's the most believed theory? Well, there is only one theory. We think that the universe arose in a violent event called the Big Bang, which by the way is not over yet. It's not as if the explosion occurred and so on. The acceleration, the expansion of the universe is the Big Bang. It's still going on, except that in the beginning it's believed to have happened in what's called an inflationary manner. So there was an exponential increase in the size, and after that it slowed down to its present value. So we have a consistent picture of what happened in the beginning related to the so-called standard model of physics or particle physics. So we know when the universe, we think, became transparent, what happened initially was the quarks and gluon mixed up in a soup called the quark-gluon plasma, and at some stage nuclei formed, atoms formed, the universe became transparent, the radiation could pass through. So we have a fairly detailed scenario of what happened since that time, which seems to be consistent, explains the abundance of the elements as far as we can measure it, etc. At the very origin, fundamental basic origin, like I said, below the Planck time, which is 10 to the minus 42 seconds, and the Planck length 10 to the minus 35 meters, our present laws of physics break down. We have every reason to believe, no reason to expect that they would continue to hold. So we don't know, for example, very fundamental questions like whether space and time are continuous or whether they're discrete, they're granular in nature. We think they'll become granular. We don't know if the dimensionality of space is fixed. We think it's a dynamical property, it's an emerging property. So we think also that there were extra dimensions, spatial dimensions, which curled up for some unknown reason. So there are all these hypothetical theories, but we have a fairly satisfactory picture of standard model of astrophysics, there's one, which explains what the evolution of the universe is after the initial violent event. So you have read this book called The First 3 Minutes, so by Stephen Weinberg, which explains very clearly how this universe evolved. But like I said, the origin is still, at that level, still shrouded in mystery.
So you told that there is a black hole in the center of every.
Yeah, we expect there's a black hole at the center of it.
But won't that black hole suck all the?
Yeah, it does. It does. I mean, things are going around and so on. Not everything will fall into it. There could be things in orbit around it. But yeah, eventually, yes. Depends on what its evolution is, whether it's expanding.
So your views on consciousness creating reality and how scientific it is.
Pardon me?
Consciousness creating reality.
Uh-huh.
And how scientific it is.
In what sense?
There is some double-slit experiment. So there is some experiment. They are trying to understand how consciousness creates reality. You had mentioned in one of your interviews in Quest magazine about this.
Well, yeah, I mean, the jury is still out on the true nature of quantum mechanics, like I said. So, the role of the observer and the observed, and a quantum theory of measurement, the satisfactory, fully satisfactory theory of the quantum theory of measurement doesn't exist as yet. So, this question of do physical events happen because of an observer's intervention, the very act of observing? These are partially answered questions. So, consciousness is a different thing altogether. Now, what consciousness is itself is not understood. We don't have an understanding of what the meaning of consciousness. So whether it creates reality is a philosophical question, which I think is too premature to talk about at the moment. Yeah. It's not in the ambit of science as we know.
I'm traveling in a bus 100 kilometers speed.
Pardon me?
I'm traveling in a bus 100 kilometers speed.
Okay.
So a small fly like E. So it is also traveled with me without touching anything. But the same fly outside the bus. That is stay outside. But the fly comes with me. What is the reason?
Well, the air is traveling with you. It's relative velocity, right? I mean, this is if that were not true, if this were not true, then everything would fly off the earth. So one often wonders, if the earth is spinning around, why is it that the trees are not being blown away completely? It's not only the solid part of the earth that's spinning around, it's the atmosphere too. So everything is going around. So when I'm in a bus, the air is traveling along with me in the bus. Right? You open the window and leave the fly near the window, then of course it sees the stream going the other direction, very likely it will be pushed out. But otherwise, if it's inside the bus and there's no current on it directly, then it's going to travel with you.
Hey, hold on.
Actually, in 1 lakh people dream their future. Accordingly, when we dream, we only remember 10% of it. How do they remember the whole future dream, and how is that any mental illness, or is that?
No, what do you mean they remember the future?
No, some people dream their future.
Is that right?
Yeah, of course, one of the family members.
They dream of the future and it comes true?
Yeah, of course it comes true.
Of course. We've solved the problem of what's going to happen in future. We just have to record this person's dreams and that's it. Do you believe that?
Yeah, of course, even my friend told about.
Oh, you believe it because your friend told you that?
No, she dreamed about going to Max Muller Bhavan and writing some German exam. But me and my friend really went to Fitman.
What does that prove?
Yeah, she told it the day before, the 1 month before, but we seriously went after 1 month to the Max Muller Bhavan. It's truly happening.
Alright. Okay. Alright. So she has a friend, she's got a pipeline into the future. She has a friend who will keep 1 month and know exactly what's going to happen. I mean, I'm not making fun of you, but you see, first of all, anecdotal evidence is not evidence. Just an anecdote. Then there are things called coincidences. And then there are things like, this is not about predicting the future. The point is, when your mind is thinking about something, and then you go to sleep, the mind is still processing that information. It's still coming up with correlations and so on, some of which you remember when you wake up, right? So you wonder how you thought of this and then it happened, because you've been working on it. Right? And then you work towards it. So it's a very complicated thing, but I don't think there's anything such as unambiguously predicting the future based on things. Just as I don't think the future is written in palm leaves or on the palm of my hand or on the stars. I don't believe that.
Can black holes suck up a whole galaxy?
Yeah, can black holes swallow up a whole galaxy? Yeah. Potentially, yes. Yeah.
If there's a black hole in the Milky Way galaxy, why couldn't the black hole suck up black?
Well, stuff is falling in. But you know, the strange thing about black holes is now we're getting into the technicality of what a black hole actually does. If an observer moves towards a black hole, falls in, apart from the tidal friction which tears them apart and so on, you could ask, what does this event look like to a person who's standing outside and looking at it, and the person who is falling in? The person who is falling in will cross a threshold called the Schwarzschild radius, or event horizon, and go in and get sucked into the vortex, the singularity, if there's a singularity, no question about it. But for the person outside, time slows down. So it will look as if this person is falling into the black hole, and as he or she approaches the event horizon, slows down and takes an infinite amount of time to reach the event. So it's not, so it's entirely the time flows depending on your state of motion. There's no absolute time at all. It's sort of mind-blowing, but that's one of the first consequences of relativity altogether. So it's not as if the matter is, all matter is going to suck tension. You have an orbit around it. Cannot? Well, I don't think we're in imminent danger of any particular black hole sucking up our universe. And if it is, we won't know it clearly. So don't worry. Not going to happen in the near future.
Okay, one more question. Last question.
Sir, is there any mission invented or can it be invented that the carbon dioxide can be absorbed and it can be divided, that carbon and oxygen? So oxygen will be useful for the human beings and the carbon is also actually used as fuel. So,
We got trees.
yeah, so can it be divided that carbon and oxygen can be divided?
What do trees do?
Man-made missions.
Yeah, you can imitate it. You can imitate it. And that's an interesting question, actually. Slightly different question in the same lines. It turns out that the chlorophyll molecule, it's believed its action relies or uses some deep quantum mechanics, some deep coherence effects in quantum mechanics. We've not figured this out completely, but nature has evolved this molecule which is doing this wonderful thing. It's using quantum mechanics as far as we can tell in a very, very clever way. So in the future we'd have factories which will do this kind of thing. Yeah, in principle we can transmute elements, we can synthesize new compounds, we can do all these things. But the question is, we can make water, etc. But the question is the amount of energy used to do this. If you take up more energy doing that than the final product can yield, it's not useful. Right? It's like saying, can I split water and use the hydrogen as a fuel? But yeah, but the cost in splitting the water, the cost in energy is greater than what you get from the other side. So it's not worthwhile at the moment.
Okay, if there are no questions, I really thank Professor Balakrishnan for taking his time and coming and you can see ocean of knowledge Professor Balakrishnan. I think no one to, a small guy to appreciate, but it's really very great things that you take time. Please give him a big applause.